B-2 Spirit is a strategic stealth bomber. It's a flying wing aircraft built to penetrate defended airspace, deliver weapons and return without being destroyed. Sources describe the B-2 as invisible. Radar cannot see it. No missile can track it. It flies wherever it wishes, undetected. None of that's accurate. The B-2 has a radar cross-section of approximately 0.1 square meters. That's comparable to a large bird. The aircraft itself has a wingspan of 172 feet. It weighs 336,500 pounds at maximum takeoff weight. Radar can detect it. The question is, how much time that detection buys the defender? In most cases, the answer's not enough. That's the operating principle of this aircraft. The B-2 can't physically disappear, but it can compress the enemy's decision-making clock until no time remains to act. To understand how it does that, we need to examine the aircraft itself. The B-2 has 4 major systems that produce its low observable capability. There's the airframe shape. There's the radar-absorbing material coating. There's the thermal and acoustic management system, and there's the electronic warfare suite. Each one works independently, but together they reduce the enemy's available response time across every detection method simultaneously. Shape matters most, because if this system fails, nothing else matters. At the front of the aircraft and at every edge, the geometry of the B-2 is designed around a single principle: radar energy that strikes the aircraft must not return to the source. A conventional aircraft has vertical tails, a cylindrical fuselage, and engine nacelles. These surfaces reflect radar energy in many directions, including back at the emitting radar. The B-2 has none of those features. There is no fuselage. There's no vertical tail. The entire aircraft is a single, blended wing with no protruding surfaces. All leading edges are aligned at the same angle. All trailing edges are aligned at the same angle. Every panel door, every hatch, every seam follows those same angles. This concentrates radar reflections into a narrow directional spikes. Unless a radar is positioned at one precise angle relative to the aircraft, it receives almost no return energy. Early stealth aircraft, including the F-117 Nighthawk, used flat-faceted surfaces to control those reflections. The B-2 uses smooth curves instead. By the time the B-2 was designed, computing power had advanced to allow supercomputers to calculate curved surface geometries that no designer could produce by hand. The result is a shape that gives radar energy almost nothing to grip. The engines present a particular problem. A jet engine's compressor face is one of the strongest radar reflectors of any aircraft. On the B-2, the 4 General Electric F-118 GE100 turbofan engines are buried deep inside the wing. Air passes through S-shaped internal ducts before reaching the compressor faces. A radar beam entering the inlet cannot travel the curved path to the compressor. It strikes the duct walls and scatters. The weapons are carried internally as well. 2 internal bomb bays sit beneath the center section of the aircraft. The B-2 can carry up to 40,000 pounds of ordnance. That includes up to 80 GPS-guided 500-pound bombs or 16 nuclear gravity bombs. External pylons would create radar reflections. The weapons remain inside until the moment of release. But shape alone is not enough, because even a perfectly shaped aircraft will reflect radar if its surface isn't managed. And managing that surface turned out to be the most demanding problem in the entire program. Across the entire outer surface of the B-2 is a layer of radar-absorbing material known as RAM. The primary active material is carbonyl iron powder. When a radar wave strikes this coating, the carbonyl iron powder converts the electromagnetic energy into heat. The wave is absorbed and dissipated. The RAM is applied in multiple layers. Each layer has different electrical properties. The outer layer is designed to be as electromagnetically similar to air as possible, allowing radar energy to enter the material rather than reflecting off the surface. Inside the layered structure, the waves are trapped and cancel through destructive interference. This coating is sensitive to environmental conditions. It is hydrophilic, it absorbs water. Rain, humidity, salt air, and heat all degrade its performance. Bird droppings can compromise the radar signature of a $2 billion aircraft. Even small imperfections change the cross-section in ways that could be lethal in defended airspace. After nearly every flight, ground crews perform extensive inspection and repair of the coating. Technicians apply the material by hand. Some sections require tape. Some require cork-like compounds that take hours or days to cure. In September 1997, each hour of B-2 flight required 119 hours of maintenance. By comparison, the B-52 required 53 hours and the B-1B required 60 hours per flight hour. Every 7 to 9 years, each B-2 undergoes programmed depot maintenance. The aircraft is stripped to the frame and rebuilt. This process took 470 days, since reduced to 379. The ram coating is removed with crystalline wheat starch, then reapplied from the very beginning. Because the coating cannot survive outdoor exposure, every B-2 requires a climate-controlled hangar. The standard hangar bay is approximately 250 feet wide, 126 feet long, and 55 feet high. When the B-2 deploys to a forward base without such facilities, the Air Force transports portable climate-controlled shelter systems. Each one costs approximately $5 million and must be assembled before the aircraft can land. Which raises a question the engineers never solved. What happens when the hangar isn't there? If you want more breakdowns like this, the engineering, the trade-offs, the things the official records leave out, then subscribing keeps them coming. On the night of February 22, 2008, a B-2 called the Spirit of Kansas was parked at Anderson Air Force Base in Guam. A monsoon rain fell overnight. A climate-controlled hangar wasn't available. The rain infiltrated the aircraft's port transducer units, the sensors that measure air pressure and calculate airspeed and angle of attack. The next morning, during pre-takeoff air data calibration, moisture in the sensor ports caused the flight control computers to calculate an inaccurate airspeed and a false negative angle of attack. The crew had no way to identify the error before takeoff. Seconds after the aircraft left the runway, the computers generated an uncommanded 30-degree nose-high pitch-up. The aircraft stalled. Both pilots ejected safely. The B-2 crashed and burned. The Spirit of Kansas was valued at $1.4 billion. It remains the most expensive aircraft crash in United States Air Force history. The cause was not an enemy missile. The cause was water in a sensor port from rain because the hangar wasn't there. This is the paradox at the center of the B-2 program. The aircraft was engineered to defeat the most sophisticated air defense systems in the world. It was not engineered to survive an unplanned night outside. The total program cost $44.7 billion for 21 aircraft. The plan called for 132. Congress cut the order after the Cold War ended and costs exceeded projections. Each aircraft costs between $130,000 and $169,000 per flight hour to operate, making it the second most expensive aircraft in the United States Air Force inventory. The idea behind this aircraft is older than anyone involved in building it, and the man who first had it died never knowing whether it had been worth anything at all. In the 30s, an aircraft designer named Jack Northrop believed that the ideal bomber was a pure flying wing. No fuselage, no tail, minimal drag, maximum efficiency. He spent decades developing that concept. In '47, his YB-49 jet-powered flying wing flew for the first time. During those test flights, observers noted that the aircraft nearly disappeared from radar returns. Nobody understood why at the time. In 1949, the Air Force cancelled the program. Every prototype was scrapped. Northrop spent the following decades attempting to understand what had happened and why his design had been eliminated. By the late 70s, Northrop was in failing health. He could not walk, he couldn't speak. He'd spent 30 years watching other aircraft designs dominate, while his flying wing concept remained buried. In April 1980, the Air Force granted him special security clearance. He was brought to a secure room and presented with a scale model of an aircraft then in secret development. And he held the model. He said, with tears in his eyes, "I know why God kept me alive for the last 25 years. The aircraft in his hands would be designated the B-2 Spirit. The design, scrapped in 1949, had become the foundation of America's most advanced bomber. The flying wing that radar could barely see in 1947 was, 30 years later, the entire point." Northrop died in February 1981. The B-2 made its first flight on July 17, 1989. The B-2 made its combat debut in 1999 during NATO's Operation Allied Force over Yugoslavia. 6 B-2s flew non-stop from Whiteman Air Force Base in Missouri. The round trip was approximately 30 hours. These 6 aircraft flew 50 of NATO's 34,000 total sorties, dropped 11% of all bombs, and destroyed 33% of selected targets in the first 8 weeks. That mission also marked the first combat use of GPS-guided JDAM smart bombs. In October 2001, B-2s flew 44-hour missions from Missouri to Afghanistan and back, requiring multiple aerial refueling contacts over the Pacific. Major Melvin Day Isle and Captain Brian Neal flew the Spirit of America on one of those missions. Day Isle later described the dynamic targeting environment. 70% of targets changed from the moment we took off. 5 target areas in one mission. In January 2017, 3 B-2s struck an ISIS training camp near Sirte, Libya, loitering over the target area as the mission evolved. Total time in the air reached approximately 34 hours. 15 aerial refueling tankers supported the mission. In October 2024, B-2s struck 5 underground Houthi weapons storage facilities in Yemen using GBU-57 massive ordnance penetrators. The GBU-57 weighs 30,000 pounds. The B-2 is the only aircraft capable of delivering it. The strikes were staged from RAAF base Tyndall in Australia. In June 2025, 6 B-2s dropped 12 GBU-57 bunker buster bombs on Iran's Fordow fuel enrichment plant. A 7th B-2 dropped 2 GBU-57s on the Natanz nuclear facility. This was the largest B-2 combat operation in the aircraft's history. Across all of these conflicts, the B-2 has never been destroyed by enemy fire. But that record, impressive though it is, has a limit, and that limit is where the threat exists. There are radar systems capable of detecting the B-2 at range. Low-frequency radars operating in the VHF and UHF bands between 30 and 300 MHz emit wavelengths that approach the physical dimensions of a large aircraft. RAM coatings optimized for higher frequency radar bands are less effective against these longer wavelengths. Russia's Nebo-M system and Iran's Ghadar radar operate on this principle. In 2012, Air Force Chief of Staff General Norton Schwartz told the House Armed Services Committee that the B-2's stealth technology was 80s vintage and that the aircraft would, over time, become less survivable in contested airspace. However, detecting the B-2 at range and tracking it precisely enough to guide a missile are 2 different problems. Low-frequency radars can identify that a stealthy aircraft is present within a broad area. They cannot generate the targeting resolution required for a missile intercept. Weapons quality tracking requires higher frequency fire control radars, and those radars are vulnerable to the B-2's electronic warfare suite. At the wing edges of the B-2 are high sensitivity antennas concealed within the aircraft structure. These form the defensive management system. The DMS detects hostile radar emissions from hundreds of miles away, maps their positions, and displays a threat picture to the crew. When the B-2 approaches defended airspace, it enters an operational mode in which antennas retract, certain communication links close, and the use of flight control surfaces is restricted to reduce radar signature. The aircraft uses passive electronic support measures to navigate through gaps in radar coverage, regions where the geometry of multiple radar systems leaves areas of reduced detection probability. When enemy radar does acquire a return, the B-2's electronic warfare suite can capture the incoming radar pulse, manipulate the signal data, and rebroadcast an alternative signal that produces false target returns on the enemy's radar screen. The aircraft's position is masked by returns indicating it's somewhere else. The engines contribute to thermal and acoustic signature management as well. Every system on this aircraft exists to close the same window. The inlets are mounted on the top of the wing. Air flows through an S-shaped duct to the 4 turbofans buried inside the airframe. On the rear of the aircraft, exhaust is expelled over a flattened titanium and carbon fiber surface. Secondary inlets scoop cold air from around the aircraft and mix it with the hot exhaust, diffusing the heat plume before it exits. The B-2 has no afterburners. Its maximum speed is approximately 628 miles per hour, high supersonic. A supersonic aircraft generates a sonic boom, propagating across hundreds of miles, and produces intense heat plumes from afterburner exhaust. Both are detectable by passive acoustic and infrared sensors. The B-2's designers chose to eliminate those signatures. There's also a contrail management system. At altitude, jet exhaust condenses into visible vapor trails that can be observed visually or by satellite. The B-2 carries a lidar sensor that detects contrail formation in the air ahead of the aircraft. When contrail conditions exist, the sensor alerts the crew to change altitude. All of these systems operate simultaneously. Radar is attenuated by shape and coating. Infrared is suppressed by exhaust mixing. Acoustics are reduced by buried engines. Visual signature is managed by contrail avoidance and low-altitude routing. Electronic emissions are minimized in stealth mode. True invisibility is still impossible for the B-2, but the effect is a simultaneous reduction across every detection method available to a defender, compressing the window of detection, identification, tracking, and engagement until it is shorter than the engagement chain requires. The B-2 is scheduled for retirement by 2032. Its replacement is the Northrop Grumman B-21 Raider. The B-21 incorporates lessons from 3 decades of B-2 operations. Its stealth coating is more durable and less sensitive to environmental degradation. It does not require a specialized climate control hangar for every deployment. Its architecture is modular, allowing system upgrades without full rebuilds. It is designed to address the low-frequency radar vulnerability that the B-2 cannot defeat. Every structural weakness of the B-2, revealed across 26 years of operations, is a design requirement in the aircraft that will replace it. And if you want to see a video about the B-21, make sure you subscribe so we can make it. And in the meantime, why not check out this video here for more great military content.